name is Hazem Gaber, and today we're going to learn how to write regular expressions. So, most languages have regular expressions, and the regular expression is it's kind of an algorithm or syntax for being able to search. So, when you write the star, generally in Windows, that means that you're looking for any type of text. So if I'm looking for a Word document, I might write star.docx, and this will match any file name with a star. I mean, any file name with a docx extension. But what if we took this idea and put it on a large scale to be able to search for any kind of pattern and also to be able to replace data based on a pattern? Um, PHP has a good regular expression system, and Perl has a really, really good regular expression system. Most languages have some kind of regular expression, and it's hard to do. It's hard to write good regular expressions, and what we're gonna find is um, you can. It takes a lot of computing power to search for data. So the more complicated your expression is, the more computing power it's going to take. So if I write an expression and it takes 10 steps to search, and you write an expression and it takes 20 or 50 or 80 or 100 steps, then your code is vastly inefficient. And if you're paying for cloud servers to run your script, then you're going to be paying a lot more money to do the same, to achieve the same result. So think about what you want to do and practice on a subset of data. Sometimes a single expression is not enough to accomplish a task, or it may not be easy enough to um, find the pattern. You may have to come up with a more complicated strategy for achieving the result that you want. Maybe you have multiple expressions. Maybe you may need loops or if statements or other types of structures as well. So there's a lot of websites online, like this one. I think it's regex.net, and you can go onto this site and paste your expression and paste some sample data. So at the top here, we write our expression, and then here we write some data, and it'll highlight the matches in real time, and it'll show you exactly um, where your expression works and where it doesn't. And if your expression takes the computer like 8,000 steps, then it's going to tell you, hey, your expression sucks. Try something else. So when we're matching, you're going to find that there's two types of expressions. Some are greedy and some are lazy. And the difference is that um, a greedy expression keeps searching through the data to match the maximum. So if I say, if I have a sentence like the cat in the hat, and my expression is star, match a character, match some text. A lazy expression would just match the T, because it'd say, hey, I matched something, whereas a greedy expression would match the um, entire sentence. Because, or if I had a lazy expression to say, uh, match any character except a white space, then the lazy expression would match the T, and the greedy expression would match the word the. It would stop when it saw the space. So when you build your expressions, you want to think about type of match that you want. Sometimes with what called recursion, the operator will be looking at matching and then reversing, and that adds to a lot of steps. We usually store our regular expression results in a two-dimensional array. So whatever our result is, we can process the data from that array just like we can with any other uh, array. We can use a for each loop, for example. When you run your expression, test it out, and look at the structure of the array. That's going to show you the kind of data structure that you're going to end up with, and then you can process it further. So let's go over some types of regular expressions. And the first type is period. The period matches any character except a new line. So in my case here, I have hello world. That's my string. So this is what I'm going to search for. And I'm writing an if statement to say if the string matches a regular expression of 5. So I've put 5 dots here. So that means that I'm asking the regular expression to see if we can match at least 5 characters in a row. And since we match any character with a dot, then our regular expression is going to match the word hello. Because that's a dot, that's a single character, it's a single character, single character, single character, and it's going to stop. So we're just saying if we match, then just output the length. We don't really care in this about the actual content. Now we can use parentheses to group elements if we're trying to return a value. So if I've got a dot, so in my case here, we've trying to match two words. So we've created H dot 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 O dot dot. So this is going to match the H in hello world. This is going to match the E. This is going to match the L. And then this is going to match the L. And this is going to match the O. And this is going to match the space. And this is going to match the W. But what's going to happen is our system is going to take out these two matches. And so if this was an array, we might have two matches like this. It shouldn't be an underscore though, it's just a space. So that's the match that we receive. Now, if we want to be more efficient, we can add a plus, and this is a greedy operator. So plus matches as many of the previous element, and we're gonna find there's more than just a dot. But in this case, so we can write a regular expression using a standard character. So in this case, I'm matching L plus. So that means I want to match the letter L as many times as possible. So obviously the word hello, we match the L twice because the first L is matched and then the second L. Now if I wrote hello, then I could write an expression, for example, L plus dot plus O plus. Now what would we get here? We'd match. Let me rewrite this. Let's say I got the word and I wanted to match the hello. I could write an expression L plus O plus. This would match. So the L plus would say, hey, I matched the first L in this, and then match the previous element as many times as possible. So I'd end up matching all the L's. And then my second set would match the first O, and it would match all the O's, and we would end up with an array equals L, 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 and 1 would match O, 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 O. Or what if I said match L plus dot O plus? Now our first set would match the L's, and then our dot would match the first O, and our second bracket would match 3 O's. So we'd end up with array 0 equals and 1 equals O, O, O. So a plus tells us to match the previous element. What did I do here? Match 1 or more times. Next slide. Now, this shouldn't be a plus, that's a typo. It should be a question mark. So a question mark matches a previous element 0 or 1 times. So this gives us an option. So in this case, we got hello, and we're trying to match the H and then a dot, question mark, E. So we match the H in hello, and then the dot says match any character, E, and then the question mark says, well, let me backtrack. So if I wrote hello, and I wrote my regular expression as H dot E, this would fail because the H would match the H and the dot would match the E, and then the E would have nothing to match. So this expression would fail. If I had H E E L L O, the H would match the H, the dot would match the first E, the E would match the second E, and this would be okay. Now, in this case, I have hello, and I have H dot question mark E. So the question mark is operating on the dot. So the H is matching the H, and then the dot question mark is its own operator, and it's matching the invisible space between the H and the E. So what happens is, this is where we get into the recursion. So what the computer does is the H matches the H, the dot question mark matches the E, and then the E has nothing to match. But since this is 0 or more, then the computer goes back and asks, well, what if we don't need this? And then does the E match? So yes, the E matches. And so we end up with our match. So our array becomes H, E. The problem is, once you start using this operator multiple times in the same expression, then the computer has to keep going back and trying different combinations of matches to see if any of them make sense, and picking the best one. And this is where you have to be careful, because you could build an expression that's either gives you the wrong result, the result not necessarily the result that you want, or it gives you the a very inefficient result that takes a long time to execute, or that consumes a lot of compute power. Now, in this other example, we've taken L dot. So remember, dot is matched as 0 or more, or 1 or more times, and then plus is 1 or more, and then the question mark is 0 or 1. So what we're saying is match the L, and then match some other expression as many times as possible, and match it 1 or more, or 0 or more times. So with respect to hello world, the L matches the L, and then the dot plus matches the LO. It doesn't match white space. So we end up with an array that says LLO. You've seen the star. So the star applies to the previous element, and it matches it 0 or more times. So in this case, hello and we're matching EL star 0. So we match EL, and then we match, the star says match the EL 0 or more times. So in this case, we matched it 1 time. Actually, we've matched the L 1 time. So, and then we've matched the O. So we end up with array equals 0 equals E L L O. So as you can see, if we've had all of these are possible matches, an E with any number of L's, and then an O, because we're saying match L 0 or more times. Now, if we wanted to match a minimum or a maximum, we can use the curly brace. So in this case, we're asking the equation to match L a minimum of 1 time and a maximum of 2 times. So hello works, heyo does not work, hello works, hello does not work. So we can put any element we want within a curly brace, and we can put the minimum and the maximum. Now you don't want to put well, I guess you could put 0 if you want to. And then we can also match up. We can also use OR, so we can match hello, hi, or pogo. We can use the OR operator. This is the same OR operator that we use in any other type of logic. We've also got the word boundary /B. So when we add a /B, we're saying we're looking for a word that ends with whatever. So we've got some kind of character set and then /B. So in this case, if I'm matching the end of hello, then I've set LLO/B. So the first thing the computer will do is it will say, let me look for L, and it matches L. And it says, does the next character contain an L? And it does. And does the next character contain an O? And it does. Does the next character the end of the line or a white space? And it does. So this matches. If I had hello, then it would match the first letter, the second letter, the third letter, and it would fail. So it's got to be the end of the line or space or end of the string. Now /W matches any alphanumeric character. So A to Z in capitals or 0 to 9 or the underscore. It does not match special characters like a semicolon, a space, this is a space, hashtag, whatever. None of these match. A capital W matches any non-alphanumeric character. So spaces, semicolons, special characters. And if you wanted to match any character, you could actually write W or W. But don't do that because you could just write the star. Because this is way more inefficient, because now a computer is doing 2 checks every time it's executing your statement. If we just want to match white space, we could put a /S. So tabs, line feeds, form feeds, spaces, character returns, next lines, variable with spaces. We can, so in this case, they've written S dot star, oh, sorry, slash s. So we're trying to match as a space, I should say white space, and then we're trying to match any character one or more times. So we're asking if we find a space. And then the capital S matches anything but the white space. So this is the opposite of the small s. So that's easy to remember. So we got slash big S, and then again the same operator. The slash D matches a digit. And remember the plus was one or more, so if we have slash D and we're matching 99, we'll match the first 9, and then the plus tells us to, since it's greedy, it'll keep looking. It will say, hey, is the next number also a digit? And if we had another 9, it would say, was the next number a digit? It'll stop when the next value is not a digit. And of course, capital D is a non-digit, so it's just the opposite. And then we can match the beginning and the end of a string or a line, and we do that with the caret. I think it's called a caret. This says the beginning of the line. So in this case, we're matching HE. So this expression doesn't really run very long because it says hello world. And so the caret says checks the beginning of the line. And then it says, is the next character a capital H? Which it is. Is the next character an E? Which it is. And then we've concluded the end. Versus the dollar sign matches the end of a line. So if I go RLD dollar sign, now depending on the logic of the software, the computer should, a good algorithm is going to start at the end and say, is this the end? And let's backtrack. What's one character previous? Is that a D? And then the next one, is that an L? The next one, is that an R? And we've got our answer. We've also got slash A and slash Z, which tell us the beginning or the end of a string. So the end of a string may be the end of a line too, but not necessarily. So if we match a slash A, then we know we've got the end. Let me backtrack here. So slash A and hello world and H. So we're looking, is this the start of the string? Yes, it is. It also happens to be the start of the line. Now, if it wasn't the start of the line, it would still match. But generally, the start of the line is the start of. So somebody put the slash n here so they could make a new line. So there's no white space here. And why this is relevant? Because we actually wrote hello world. So if I wrote slash a w, the A would not match right here because this is a new line that's not the new string though. It would only match up here. So it would be looking that the next letter was an H. if we had written what was it again? The beginning of, if we had written a caret W, then we'd match. Let me write this again. If we wrote hello world caret W, we'd match the beginning of the second line and then the W. And if we wrote caret W or caret H, then we'd match both of them. So we'd match the W and we'd match the H. And then the same goes for /Z, which matches the end of the line. I mean the end of the string. So /Z, in this case, the end of our string is a /n, which tells the computer to start a new line. So this person has tried to match D /n/Z. So the D matches the D, and the /n matches the /n, and the Z matches the end of the line. Now we can put a bunch of letters in a square bracket and match everything but those letters. So what we've done is we've with a caret, of course. So caret ABC says match everything but letters A, B, or C. So when we wrote hello world, and if it doesn't contain it, the computer's checking this, and this is massively inefficient because it's checking every letter in every white space, and it's doing it with every single character. So before you use this, think about it. Is there a better way to match what you're looking for? Because this is going to take us forever, especially with a very large string. And you can put any characters you want in here. As soon as the system hits a match, it'll stop the search. So this is kind of saying yes or no. There's a lot of better ways to write this kind of expression. Any questions? Please leave a comment.